Recently, I was presented with another interesting question. Kevin asked about preferred queue and deque data structures in Java, and whether one should avoid a deque when a simple queue was all that was needed. A deque, by the way, is simply a double-ended queue. In this video, I'm going to take a look at this discussion. There are several considerations when choosing a data structure for any given purpose. First, perhaps obviously, does it do what you need? Then you might ask, is it computationally efficient for the use cases you envisage? Is it space efficient, that's memory use, for those use cases? How easy will it be to change the selected structure if the use cases change or perhaps were misunderstood? Do you need thread-safe access to it? Now, for the sake of keeping this video to a reasonable length, I'm going to say that concurrency is way too complex to address here, so we'll ignore that one. It's really quite unlikely, though, that a thread-safe structure will perform better than a non-thread-safe one in a single-threaded environment. It might not be much worse, but it's a safe assumption that thread safety will have some costs, and if there's no benefit to offset those costs, we should avoid such structures. For example, vector and string buffer have been part of Java's core libraries since Java 1.0. Well, actually, they were in the pre-releases. They're both thread safe, and they both note that alternative classes are recommended if that thread safety is not needed. If we want a queue, we almost certainly want to have something that implements the interface queue. Faking it with something not intended for the purpose is usually a bad idea. Although in some situations, if only a small subset of the functionality is needed, perhaps it's something to consider. An example of this not being a great idea is if you try to use a list structure, particularly an array list. We'll have a quick look at the array list before we're done and see this really is a bad option. Similarly, if we want a double-ended queue, we're looking for an implementation of the interface deque. Generally speaking, if we're choosing a concrete implementation of a conceptual structure, and different concrete structures might have different behaviors, different performances, if you like, in different usage scenarios, we should program to the interface, not the implementation. This allows us, at least in theory and in the great majority of cases in practice, to swap out the implementation without having to make changes in consequence to the rest of our code base. This way, if we discover we made the wrong choice, or perhaps if the usage pattern changes after deployment and the new usage pattern renders the structure less than ideal, we can slip in the new structure quickly and just move on. So, what choices for concrete implementation of queue and deque exist? Well, let's take a look at the API and decide what choices are actually available. The API docs for the deque interface show ArrayDeque and LinkedList, and two classes that are in the concurrency APIs, so we'll ignore those. If we look at the ArrayDeque, we see it also implements the queue interface, and that's also the case for LinkedList. Indeed, deque is a sub-interface of queue. So these two are contenders for either concept. If we look at the classes that implement queue, we see, of course, ArrayDeque and LinkedList, but then we also have abstract queue. Well, that's abstract, so not usable unless we code up a concrete subclass ourselves. Then we have array blocking queue, concurrent linked deque, concurrent linked queue, delay queue, linked blocking deque, linked blocking queue, linked transfer queue, priority blocking queue, and synchronous queue. All of these are members of the concurrency APIs, so they're thread safe and we'll be ignoring them. There's also priority queue. This one doesn't provide a simple first in, first out behavior like a normal queue, but it actually sorts items so that lower values move further toward the front of the queue. This is a different behavior that you either want or you don't, and if you don't, it's a simple choice to avoid it. So this actually leaves us with nothing more than ArrayDeque and LinkedList that would be capable of fulfilling a need for either a queue or a deque. So how do we choose between these two? At this point, the next consideration to come up would probably be performance. There are a couple of ways of approaching this question. The first, and undoubtedly the most accurate, is to build out your production code, instrument the feature of interest, in this case the deque, and measure the performance of each of the alternative approaches under conditions that are as realistic as possible. Realistic in terms of deployment environment and load. That's not usually terribly practical, certainly before you've started, but it might be more so if we relax the realistic conditions part and just make tests that exercise the features we expect to use. Sometimes even that's too tiresome, and another approach is simply to consider how the implementations might behave when used in the way we anticipate, and get a feel for them at a conceptual level. What's in the way you anticipate mean? Well, perhaps you expect to add many items to the queue, making it grow very large, and then remove lots of them, shrinking it back down again. Or perhaps it's more likely that you'll have a few additions, followed by a few removals, with a relatively steady overall size, and perhaps a relatively small size at that. Things like this can make a difference and should be considered. Now, you might be tempted to do a full complexity analysis. That's the big O notation stuff. But that's actually more about how an algorithm scales than how fast it is. And the two aren't exactly the same thing. An algorithm with a bad complexity could be faster than one with a good complexity, especially for smaller data sets. And you must consider how your data is expected to behave, and indeed, how confident are you of that estimate, both now and into the future. So, we have a linked approach and an array-based approach. Let's consider how these look. For now, by the way, those of you that know how the ArrayDeque works, I'll be misrepresenting it initially. But that's because I'm telling a story and want to encourage caution about making assumptions. Bear with me, we will get to the truth. So, in a linked structure, each element is wrapped in another object that maintains a reference to the next element in the sequence. The structure keeps a reference to at least one end of the data sequence. Some variants keep a reference to both ends, and in that case, each element will have a reference to both the previous and next elements. Notice that if one of these references is null, that will mean that we've reached the end of the sequence in that direction. The terms singly linked and doubly linked are used to describe these variations, and Java's linked list is doubly linked. So, to insert a new element at the tail, we put the new element in the wrapper, find the tail marker, and use that to find the last valid element in the existing dataset. Then we set the next reference in that previously last element to point at our new element. Now we set the next reference of the new element to null to indicate that it's now the last valid element. And then we point the tail marker's previous element pointer to our new element. And finally, we set the previous element marker of our new element to point out what was previously the last element. Now, that's not particularly difficult computationally, but we must make one new object, the wrapper, set the wrapper to refer to the new data item, and set the value of 4 references for the various links. What happens when we want to remove an element from the other end? Well, we find the head marker, identify the next element. We'll need to keep track of it so as to be able to pass it back to the calling code. Then we find the next object, which is about to become the first in the sequence. We set the next reference of the head to refer to that new first element. Notice we're cutting out the object we're about to return from the sequence. And we set the previous reference to null, indicating there's nothing in the sequence that comes before this now first one. Finally, we return the data element found in the wrapper, and that particular wrapper can become garbage collectible. Again, this is not particularly computationally intensive. We've updated 2 references, followed one reference inside a wrapper to find the actual data object to be returned, and made one object garbage collectible. Also, from the point of view of complexity, the amount of data in the structure makes no difference to the count of operations performed. These particular operations are O1 behaviors, although there are several other behaviors in a linked structure like this that aren't relevant here, which are not O1. Notice I've only described adding an item at the end and removing an item from the start, but the logic of these operations at the other end is really the same. These would be the things we'd do if we were trying to build a deque. We simply swap our references in the discussion of head and tail and next and previous. So the next thing to consider is what might it look like if we use an array to build a queue? Well, a naive or bad implementation might treat the 0 index of the array as the head of the queue and use a count variable, probably of int type, to describe how many elements are in the queue while allowing the array to have spare capacity. In this case, the element at the count-1 index is really the tail of the queue. We'll look at the single directional queue first, and I think it'll be fairly clear how a double-ended approach could be handled. Adding an element is pretty easy. Set the array element at count to refer to the new data and increment the count. Of course, things get messier if the array has no spare space. We'd have to allocate a new, larger array, copy the items across, and then do the insert. This whole description is, of course, simply what the ArrayList does if we add more data to it than the existing storage can handle. If we have a lot of data in the array, then all that copying will become expensive in proportion to the number of elements to be copied. That's O of n, of course, but that is not the worst of our troubles. Removing an element in this model is ugly. We need to grab the reference from index 0, hold on to it so that we can return it to the caller when we're done. But then we must move every item of the array to a new position at one subscript value less. And we just mentioned that copying array contents gets expensive when the array has a lot of data. If you're going to try to make a queue out of an array using this approach, the performance will be horrible. Fortunately, this isn't what the ArrayDeque does, but it's important to realize that if we tried to use an ArrayList as a queue, this is probably how we'd do it naively, and the results would be terrible. Now, if you poke around in the source code for ArrayDeque, you discover that while this class is built on an array for storage, it uses that array in a structure called a circular buffer. Now, in a circular buffer, a linear array is treated as if the highest index is followed by index 0. So it's kind of like the array is curled around on itself. This is, of course, a logical rather than literal idea, but it works very nicely for a queue and can work as a double-ended queue equally well. Let's take a look at adding items. There are two counters. Let's call one head and one tail. These are associated with the structure. In this example, the tail is where the next item will be appended, and the head is where the next item to be removed will come from. Let's start with two data items in the middle of our storage array like this. The head index has value 3, which points at the number 9. The tail index has value 5, which means that there are two live items in the array, being the numbers 9 and 10. The remaining indexes do not have valid data in them. To add an item to the end of our queue, let's add 12. I'm not sure why I can't count. We'll simply store it at the index tail. Then we'll increment that index. For removal from the front of our queue, we take the item at the head index and then increment the head index. The queue is empty if the head and tail indexes are the same. Of course, as we add more data to the end of the queue, we reach the end of the real array for storage. At that point, we start again at the beginning, provided it's not full, but we'll investigate that in just a moment. This calculation is essentially a modulus or remainder operation. 7 plus 1 is of course actually 8, but we calculate the remainder after a division by the array length, which in this example is 8, and we get back to 0. As a side note, Java uses percent as remainder, not modulus, mod. But with two positive integer operands, mod and remainder produce the same thing. Now in this model, we'll treat the queue as full if incrementing the tail index would make it equal to the head. This means that this structure actually has at least one unused slot at all times. Now the reason for this is that we've already specified that if the head and the tail have the same value, then the queue is empty. Unless we keep another flag, we can't use the same test, the head and the tail are the same, to represent both full and empty. That would just be confusing. Now, given this outline, notice that adding an item requires writing one reference value into the array and then incrementing one of our counters modulo the size of the array. Incrementing modulo something is a little more complex than simple addition, but it can be particularly efficient if the array size is mandated to be some exact power of 2. Hopefully it's clear how we can run this queue in reverse and create a double-ended queue, or deque, without compromising its performance as a single-ended queue. This structure is what's in the ArrayDeque in Java's libraries. Now I've run some tests and found that approximately the throughput of the ArrayDeque for simple add and remove operations is actually about twice as fast as the linked list. Using the ArrayList, pulling from index 0 and adding at the index of the count, by contrast, rapidly slows down as the number of items in the queue grows. Of course, the ArrayDeque does have to reallocate and copy, unlike the linked list, and it'll do that at intervals as and if the count of items grows larger. But it's actually pretty smart about how it does that, growing in big chunks to reduce the number of reallocations needed. Now soon I plan to make another video demonstrating a couple of different load scenarios and making timing comparisons of linked list, ArrayDeque, a simple hand-coded circular buffer, and the naive use of ArrayList that I described and warned you would behave terribly. Don't forget to subscribe so you'll hear when that's released. Meanwhile, if I could ask you to add your comments, in particular, let me know if there are topics you think would make an interesting and helpful video, and don't forget to hit like. Till next time. Cheers.